Have you ever wondered how your favorite online store seems to know exactly what you want to buy even before you search for it? Or how self-driving cars can instantly navigate complex city traffic? All of that is done because of data science. Data science is the exact intersection where a vast amount of information meets modern computing to derive meaningful information, find unseen patterns, and also solve real world problems. It is incredibly important in today's world because it allows us to take raw, chaotic data and transform into a validated, confident decisions. By merging applied statistics with computer science, data science empowers industries to automate risk analysis, predict stock market trends, prevent credit card fraud, and even accelerate the discovery of life-saving drugs. In this video, we will be discussing 6 major modules that will take you from a beginner to a fully capable data science professional. Here's a brief overview of what each module covers. Module 1 will be Introduction to Data Science and Life Cycle module. Module 2 will be Probability and Statistics. Module 3 is Data Preprocessing and Exploratory Data Analysis. Module 4 will be Machine Learning and Predictive Modeling module. Module 5 will be Data Visualizing and Communication module. Module 6 will be Model Deployment and Operationals. That's it. If these are the type of videos you'd like to watch, then hit that subscribe button with the bell icon to get notified whenever we host. Also, just so that you know, if you want to upskill yourself, master data science and data analytics skills, and land your dream job or even grow in your career, then you must explore Simplilearn's cohort of various data science and data analytics programs. Simplilearn offers a variety of master's, certification, and postgraduate programs in collaboration with some of the world's leading universities. Through our courses, you will gain knowledge and work-ready experience in skills like Python, Tableau, Power BI, Generative AI, and over a dozen others. And that's not all, you'll also get the opportunity to work on multiple projects led by industry experts working in top-tier data and product companies. After completing these courses, thousands of learners have transitioned into data science or even data analytical roles as a fresher or even moved on to a higher paying job and profile. If you're passionate about making your career in this field, then make sure to check out the link in the pinned comments and in the description box below. Hurry up and enroll now. So let's get started with our data science full course with a small quiz. Which of the following describes the primary goal of data science? Is it writing complex code using Python, storing large amount of data, extracting insights and making predictions from data, or is it creating dashboards only? Please let us know your answers in the comment section below. Now let's get started. Now let's start with the first module, which starts with Introduction to Data Science. Let's begin by understanding what data science really is. Can you observe the visual? It shows data science at the center, formed by overlap of 3 major areas: mathematics, computer science, and domain expertise. Around that overlap, we also see machine learning, statistic research, and also data processing, which tells us that data science is not just one skill or one tool. It is a combination of logical thinking, computing power, subject knowledge, and also analytical methods working together. That is why data science is much more than simply writing code or building models. It brings together different disciplines to understanding data, discovering patterns, and solve practical problems. A simple way to define it is this: data science is exact intersection where vast information meets modern computing to derive meaningful information, find unseen patterns, or even to solve real-world problems. So if someone asks you what data science is, the best answer is that it is a field that turns raw information into useful insight by combining math, technology, and domain understanding. This gives us the right starting point for the rest of the module. The main idea here is simple. Data is useless in its raw form. It must cultivate through a religious transformation pipeline to yield actionable insights. In other words, raw data by itself does not help much until it properly collected, managed, analyzed, and presented in a meaningful way. That is why a life cycle is divided into 5 important stages: capture, maintain, process, analyze, and communicate. Capture is where data is collected. Maintain is where it is stored and organized. Process is where it is prepared for analysis. Analyze is where patterns and insights are discovered. And finally, communicate is where the final findings are shared in a useful form. This flow shows that data science is not just a single activity but a complete journey. Every stage adds value and each one dependently on previous stages being done correctly. Once this life cycle is clear, it becomes easier to understand the people and the roles involved in making the entire process work. Now let's move into foundation of data life cycle, because everything that comes later depends on how well this part is handled. The first stage here is capture. Capture is defined as gathering raw, structured, and unstructured information from diverse sources. The key activities include data acquisition, data entry, signal reception, and also data extraction. So, this is the point where data first enters the systems from different sources and in different formats. The second stage is maintain. Maintain is defined as transforming raw inputs into usable, stable architecture for future modeling. The key activities include data warehousing, data cleansing, data stacking, and also data architecture. This is where the collected data is cleaned, organized, and stored in a way that makes future analysis possible. Together, capture and maintain form the base of the entire data science workflow. If this foundation is weak, every later stage becomes weaker too. Now let's move into the analytical engine of data lifecycle, where data starts turning into insights. This part of the life cycle is where the real analytical work begins. The third stage is process. Process is defined as examining the prepared data for patterns, ranges, and biases to determine modeling utility. The key activities include data mining, clustering, and classification, and even data modeling. This stage helps us understand the structure and quality of the data so we can know how it can be used for deeper analysis. The fourth stage is analyze. Analyze is defined as the real meat of the life cycle, predicting futures, testing hypotheses, and finding answers. The key activities include exploratory or even confirmatory data analysis, predictive modeling, regression, and even text mining. This is a stage where data starts answering questions, revealing patterns, and supporting predictions. So, process prepares the data for analytical use, and analyze turns the prepared data into actual insights. Once those insights are ready, the next step is to present them in a way people can understand and use. Now come the final stage of data lifecycle, and that is communicate. Communicate is defined as translating mathematical complexity in human clarity. It also explains that this final step synthesizes the information into readable formats to drive immediate business action. That means the work is not complete when the analysis is done. The real value is created only when the findings are presented in a way that decision makers, teams, and stakeholders can easily understand. The key activities involved here is data reporting, data visualization, business intelligence or BI, and executive decision making. These are the methods through which insights are shared and turned into actions. So this final stage closes the full life cycle by converting analysis into business value. And that is what makes data science practical in real world. Not just finding answer, but making those answers understandable and usable. Now that we have understood the stages of data life cycle, the next question is who actually carries out all this work? That is where the idea of human capital comes in. Data science is too broad, too complex to be managed by a single individual from start to finish. It requires an ecosystem of specialized talent working together in precise harmony. That is where four major important roles are introduced here: data engineer, machine learning engineer, data scientist, and data analyst. Each one plays a different part in a larger data science workflow. The data engineer is responsible for building and managing the data foundation. The machine learning engineer focuses on developing and scaling machine learning systems. The data scientist works on extracting patterns, building models, and solving deeper analytical problems. The data analyst focuses on interpreting data and turning it into business understanding. So, this slide makes one thing very clear: data science is not just a job role, it is a collaborative ecosystem of specialized professions, each contributing to a differently but equally important way. And once these roles are clear, the next step is to see exactly how they map across the data lifecycle. Now let's look at these roles more closely and understand what each one actually does in data science ecosystem. This comparison helps separate roles that are often confused with one another, especially by beginners. Even though all of them work with data, their focus, tools, and final outputs are quite different. The data engineer focuses on infrastructure, scalable big data ecosystems, ETL pipelines. The tools associated with this role include Hadoop, MongoDB, Hive, C++, Java, and the output is clean, accessible, stable data systems. The data analysts focus on data interpretation, mugging, and historical reports. Common tools here include SQL, R, SAS, Excel, and Tableau, and the output is visualizations, dashboard, and business reports. The ML engineer focuses on researching and designing scalable machine learning algorithms. The tools listed include Python, Java, REST APIs, and also A/B testing, and the output is automated, production-ready AI systems. The data scientists focus on predictive modeling, deep learning, and strategic problem solving on unstructured data. The tools include Python, R, deep learning, and SQL, and the output is actionable forecast and advanced insights. So this is clear that the role boundary is much clearer and shows how each one contributes in a different way. Now that the different roles are clear, the next step is to see where each one fits across the data lifecycle. This visual maps the data engineer, ML engineer, data scientist, and data analyst against the main stages of the workflow, which is capture, maintain, process, and analyze, and also communicate. The blue bars make it easy to see that every role has a different area of strength within the pipeline. The data engineer is positioned mainly around capture and maintain, which makes sense because this role is focused on bringing data into the system and building a reliable data foundation. The ML engineer stretches from maintain into process and analyze, showing responsibilities for developing scalable machine learning systems that depend on prepared and structured data. The data scientist is strongly aligned with process, analyze, and even a part of communicate because this role works on extracting patterns, building models, and generating insights. The data analyst is connected around analyze and communicate, reflecting a stronger role in interpretation, reporting, and also presenting findings to support decision making. So the big idea here is simple. Collaboration remains constant, but each role has its own center of gravity within the pipeline. That is what makes the full life cycle work efficiently as a team effort rather than as a single person job. Let's start with a simple situation. Imagine you're running an online business and every weekend you have to decide how much stock to keep ready. If you order too little, you lose customers because products go out of stock. If you order too much, you waste money on unsold inventory. Now, the big question is how do you make the right decision when you do not know exactly what will happen next? This is where probability and statistics enter the picture. Statistics helps us look at the past sales, identify patterns, summarize behavior, and understand variation in demand. Probability helps us deal with uncertainty by asking what is likely to happen, what could go wrong, and how confident we can be in a decision. Together, they help us move from guessing to reasoning. And that is why this topic matters so much in data science. Every time we forecast sales, interpret a survey, evaluate a model, run a A/B testing, or even make a business decisions from sample tests, we are relying on probability and statistics. They help us organize raw data, understand uncertainty, compare outcomes, and also make decisions based on evidence rather than instincts alone. So, as we go through this module, the goal is not just to learn formulas but also to understand how data can guide confident decisions in uncertain world. Now that we have seen why probability and statistics matter, let's understand the journey this module is going to take us through. Everything in this topic can be organized into three connected parts: the known, the transition layer, and the unknown. And that is exactly what this roadmap is showing. We will begin with the known, which is descriptive. This part focuses on raw data that we already have in front of us. The question here is very practical. What happened in our specific data set? In other words, when we collect a sample, descriptive statistics help us summarize it, organize it, and understand its basic patterns. This is where concepts like averages, speeds, and simple summaries begin. From there, we move on to the translation layer, which is the probability. This is where we stop looking at what happened and start asking how data behaves in nature. Probability helps us connect observed data with uncertainty, patterns, and likelihood. It acts like a bridge between the sample we can see and the broader reality we are trying to understand. Finally, we move into the unknown, which is inferential. Here, the question becomes deeper. What truths can be uncovered about the whole? That means we use the sample to make conclusion about large population. So the full journey is very logical. First we describe what we know, then we understand the uncertainty through probability, and then finally we infer something bigger than the sample itself. This roadmap is important because it gives structure to the entire module and shows how every topic connects to the next one. Let's start with descriptive statistics. Let's understand the difference between descriptive statistics and also inferential statistics. Let's start with descriptive statistics. The goal here is to summarize and organize existing data. Its scope is limited to specific sample in front of you. That means descriptive statistic does not try to go beyond and data you currently have. It simply helps you understand it more clearly. The key tools listed here are mean, median, mode, and variance and standard deviation. And the output is exact numerical facts such as maximum height, an average score, or a measured spread within the sample. Now compare that with inferential statistics. The goal here is to generalize and make predictions. Its scope is much broader because it is connected with entire unobserved population, not just the sample we currently hold. In other words, inferential statistics uses sample data as evidence to say something about the bigger group. The key tools here include hypothesis tests such as t-test, ANOVA, and also chi-square. And the output is not just a summary but the probability and the confidence intervals, which helps us measure uncertainty and make reasoned conclusions. So difference is simple but powerful. Descriptive statistics tells us what the sample looks like, while inferential statistics helps us move from the sample to the population. One explains what we have observed and other helps us make conclusion beyond that we directly observe. That distinction is going to guide everything that follows in this module. Now let's get to know what is descriptive statistics in detail. It is a part of statistics connected with understanding the sample we already have. Before we try to make predictions or draw conclusion about a larger population, we first need to make sense of the data in front of us. And that is exactly what descriptive statistics helps us do. A raw data often looks like chaos. It may contain dozens, hundreds, or even thousands of values, and when we look at it, it is unorganized form. It is difficult to immediately understand what is going on. That is why the first step in statistics is not prediction but summarization. We take raw data and convert it into something structured, readable, and meaningful. This process helps us extract two fundamental truths about the dataset. The first is central tendency, which tells us where the data gathers. In simple terms, this helps us identify the center of the dataset, the point around which many observations are clusters. The second is spread, which tells us how widely the data varies. This helps us understand whether the values stay close together or are scattered far apart. That visual movement from chaos to raw data to ordered, summarized data captures the real purpose of descriptive statistics. We are not changing the data itself, we are changing our ability to understand it. Instead of getting lost in individual observation, we begin to see patterns, shapes, balance, and variation. This is what makes the sample interpretable. And these two ideas, which is central tendency and speed, will guide us the next few slides. First, we'll look at how to locate the center, which is mean, medium, and mode. Then we will measure how much the data varies using variance and standard deviation. Now that we have descriptive statistics help us summarize a sample, the first major question is, where is the center of the data? In other words, if we want one value that represents the data set, what should the value be? This is where the three most common measures of central tendency comes in, which is the mode, median, and mean. The first one is the mode, which is the most frequent observation. This tells us which value appears the most often in the dataset. It is especially useful when repetition matters, such as identifying the most common product size, the most repeated survey answer, and also the most frequent category. The mode focuses on popularity rather than balance. Next comes in median, which is exactly in the middle value, and it is described here as an anchored and robust. That word robust is important because the median is less affected by extreme values. The median still stays centered on the middle position. This makes it very useful in skewed distributions such as income data or even house prices. Finally, we have the mean, which is a mathematical average. It is calculated by adding all the values and dividing by total number of observations. The mean uses every value in the data set, which makes it very informative but also sensitive to the leverage of extreme outliers. This is why in visual, the mean is pulled in the direction of those extreme points. So even though all three describe the center, they do not always give the same answer. Mode shows what occurs most often, median shows the middle, and also the mean shows the average balance point. Choosing the right one depends on the shape of the data and the presence of the outliers. Once we understand the center, the next step is to understand the other half of the story, not just where the data sits, but also how widely it spreads. Once we know where the center of the data lies, the next question is just as important. How far do the values spread around the center? Two data sets can have the same mean or the same median, yet behave very differently if one is tightly grouped and the other is widely dispersed. That is why descriptive statistics is not complete until we also measure variation. This slide introduces two important measures of spread, which is variance and standard deviation. Variance is defined here as an average of all squared deviation from the mean. That means we begin by looking at how far each data point is from the average. Then square those difference and then take their average. Squaring is useful because it prevents position and negative derivation from cancelling each other out, and it also gives more weight to values that are far from the mean. Standard deviation is square foot of the variance. That step is very important because variance is measured in square units but can be harder to interpret directly. By taking the square root, we return the measurement to the original units of the data set. That is why standard deviation is often more intuitive and easier to explain. So far, we are focused on what has already happened in the data, which is descriptive statistics. But at this stage, we are still looking backward. We are describing observation that already exist. The next step is to ask deeper question. How do we move from observed data to understanding uncertainty, patterns, and future outcomes? This is where probability enters. Probability acts as a transition layer between data and real world. Descriptive statistics summarizes what has already happened because probability helps us understand the underlying rules that generated those outcomes. In other words, if it is not about just recording results, it's about reasoning from those results. If descriptive statistics tells us a story of a sample, probability helps us understand the logic behind the story. That is why probability is such a powerful concept in data science. So far, we have focused on what already has happened in the data. Descriptive statistics help us summarize the sample, identify the center, and also measure its spread. But at this stage, we are still looking backward. We are describing observation that already exist. The next step is to ask a deeper question. How do we move from observed data to understanding uncertainty, patterns, and future outcomes? This is where probability comes in. Probability acts as a transition layer between data and real world. Descriptive statistics summarizes what has already happened, but probability helps us understand the underlying rules that generate those outcomes. In other words, it is not just about recording results, it's about reasoning from those results. If descriptive statistics tells us a story and a sample, probability helps us understand the logic behind the story. That is why probability is such a powerful concept in data science. It allows us to model uncertainty instead of ignoring it. It helps us ask questions like, how likely is this event? How unusual is this outcome? And what should we expect next if the same process continues? Once we begin thinking in probabilities, we stop treating observation as an isolated facts and start seeing them as outcomes generating by patterns, randomness, and structure. This is also what makes predictions possible. By understanding nature's rules, we can make informed guesses about what may happen next, not perfect certainly, but reason expectation. And that is a major shift in thinking. We move from describing the past to preparing for the future. So probability is not separated from statistics. It connects descriptive statistics to the inferential statistics. It is a bridge between what we observed in the sample and what we want to say about the larger process behind it. And the next slide introduces one of the most important patterns of probability, which is Gaussian or normal distribution. Now we arrive at one of the most important ideas in all of the probability and statistics, the Gaussian distribution, also known as the normal distribution or the bell curve. A normal distribution is symmetric around its center. Most observations cluster near the center. The values become less frequent as we move away from either the direction. This is why the curve rises in the middle and tapers off towards both ends. One of its most important properties is visible in the diagram. The mean, medium, and the mode all meet at the center in a perfectly normal distribution. That tells us something powerful. When data is balanced with no strong skew, the most of the common value, the middle value, and the average value all line up. This makes the normal distribution a very useful reference model for understanding how real world data behaves. The idea that Gaussian distribution appears in many natural settings is also central to why it matters so much. Many measured phenomena tend to cluster around a central value with relatively fewer extreme observations, and this bell shaped behavior appears across many statistics applications. In practice, not every dataset is perfectly normal, but the normal distribution gives us a powerful starting point for modeling uncertainty and understanding the variation. After understanding the normal distribution, the next important question is this: how do we measure where a specific observation lies within the distribution? That is exactly what z-score helps us do. A z-score tells us derivations a value is above or below the mean of the distribution. In other words, it converts raw distance into standardized statistical distance. The formula here is x minus mu divided by sigma. This means we take an observation, extract the mean, and divide by standard deviation. Once we do that, the value is no longer tied to the original units of the dataset. Instead, it is expressed in terms of standard deviation from the mean. That is why z-score are so powerful. They standardize any datasets and tells us exactly how far a point is from the center, regardless of whether the original units are marks, heights, salaries, or responsive time. A z-score of 0 means the observation is exactly at the mean. A positive z-score means it is above the mean, and a negative z-score means it is below the mean. So a z-score is not just a number, it is common language for comparison across different datasets. This concept becomes incredibly useful in statistics because it converts individual observation to a larger distribution. It helps us identify unusual values, compare scores fairly, and eventually compute probabilities under the normal curve. And that brings us to the next major shift in the module. We are ready to move into inferential statistics, where we use sample evidence to say something about a larger population. So far, everything we have done has prepared us for this shift. We started by summarizing the sample, then measured center, and then spread, and then used probability to normal distribution to understand uncertainty and the distance. Now we take the next major step, which is we move from data we process to the truths we cannot directly observe. And that is the core idea behind inferential statistics. Inferential statistics uses sample data to draw conclusions about a large population whose truly parameters are usually unknown. This slide captures that moment very clearly. On one side, we have sample statistics, which represents the data we actually have in hand. On the other side, we have population parameters, which represents the larger unobserved truth we want to understand. In most real-world situations, measuring the entire population is impractical or impossible, so we rely on representative sample and use it as evidence. But that immediate creates an important question. If we see pattern in sample, is it real signal about population or is it random variation? If we see a pattern in the sample, it is real signal about the population or is it just a random variation? That is exactly the problem in inferential statistics is designed to solve. It helps us decide whether what we observe is likely reflect of a broader truth or whether it might simply be a statistical fluke. This is where inferential statistics is probability based. Because samples vary, we never know which completes certainty how closely a sample matches the population. Instead, we make decisions using evidence, probability, and formal testing methods. And that leads directly to the next concept, which is hypothesis testing, where we begin to test claims about the unknown population using the sample we observe. Now we come to the heart of hypothesis testing, the null hypothesis and the p-value. This is a point where inferential statistics become a decision-making process. We are no longer just describing data. We are now asking whether the evidence is our sample is strong enough to challenge the existing assumption. We begin with the null hypothesis or HO. This is where baseline assumptions are default position that says that there is no real effect, no meaningful difference, or no relationship. In hypothesis testing, the null hypothesis acts as a starting point that we assume to true until the data provides enough evidence against it. It is not a claim we can try to prove forever. It is simply the position we test against. Then comes in the p-value. The p-value is the probability of obtaining results at least as extreme as the ones we observe, assuming the null hypothesis is true. So the p-value does not just tell us whether the null hypothesis is true or false directly. Instead, it tells us how surprising our observed data would be if the null hypothesis were actually correct. That is why the slide uses the image of a scale. On one side is null hypothesis, the assumed innocent baseline, and the other side is a weight of a new evidence which is represented through the p-value. If the p-value is very small, typically less than 0.05, then observed data will be quite unlikely under the null hypothesis and we reject the HO in favor of the alternative hypothesis, which is the H1. If the p-value is larger, we do not reject the null hypothesis because the evidence is not strong enough. So in simple terms, hypothesis testing is a disciplined way of weighing evidence. The smaller the p-value, the heavier evidence against the null. Now that we have understood the null hypothesis and the p-value, the next practical question is which hypothesis test should we use? In statistics, choosing the right test is not random. It depends on the kind of question that we are asking and the structure of the data we are comparing. This slides focus on common situation, which is comparing groups to find significant difference. If the answer is yes, then the next question becomes how many groups are you comparing? That single decision point is extremely important because it guides us towards the right test. If you're comparing exactly to two groups such as men versus women, treatment versus control, or before versus after, we are typically using a t-test. A t-test is designed to compare the means of two groups and determine whether the difference between them is statistically significant. If we are comparing three or more groups such as East, West, North, South, then we move on to ANOVA, which stands for Analysis of Variance. ANOVA is used when we want to compare means across three or more groups at the same time. This is important because running many separated t-tests increases the chance of false positives, while ANOVA handles all the comparison in one overall framework. Note, these parametric tests. Note, parametric test makes assumptions about the underlying distribution of the data. Essentially, that is approximately normal along with the assumptions like independence and often similar variance across the groups. So this slide gives us a practical decision rule. Two groups used led by t-test and three or more groups led by ANOVA. Next, we'll look at the idea from the previous one and turn it to one more structured comparison. Instead of only asking which test to use, we now look at why each test is used, what variables is expected, and what null hypothesis is tested, and what kind of a real-world question it makes. This makes the distribution between the t-test and the ANOVA much more practical. Let's begin with the use case. A t-test is used for comparing means between exactly two sets of data if you only have two groups. This is usually the direct and appropriate choice. In contrast, ANOVA is also used for comparing means across three or more groups. So the number of groups is the first major deciding factor. Next, look at the variables. In both cases, the setup involves one categorically independent variable and one quantitative dependent variable. The difference is that the t-test is categorical variable has two categories, while in ANOVA it has three or more categories. Now consider the null hypothesis. For the t-test and the null hypothesis is a group. One mean is equal to group of two mean. For ANOVA, the null hypothesis is that all the group means are equal to, such as group 1 mean is equal to group 2 mean is equal to group 3 mean. That is a very important distinction between ANOVA test for an overall difference. Somewhere among the groups, not just between one pair. A t-test might ask whether a new drug lowers blood sugar more than an existing drug. ANOVA might ask which region, which is north, south, east, or west, spends the most on shopping. So this slide acts like a quick diagnostic chart. Two groups suggested a t-test, three or more groups suggested ANOVA. And since ANOVA is now introduced, the next slide will break down about it. So in this slide, we'll explain the core logic behind ANOVA in the simplest possible way. ANOVA does not just compare group names or look casual at averages. Instead, it compares two kinds of variations: within group variance and between group variance. Understanding this key difference is a key to understanding how ANOVA decides whether a result is meaningful. First, look into the within group variance. This is a natural spread or noise inside each individual group. In the visual, each colored cluster has points scattered around its own center, and that spread represents the normal variability within that group. Even when the group are truly similar, there always be some random variation inside them. Now look at between group variance. This refers to how far apart the group means are from one another. In the diagram, the cluster of east, west, north are separated in spaces, and that distance represents between group variation. If the group centers are far apart, it suggests the group may genuinely differ, which is essentially the ratio of between group variance to within group variance. If the distance between the groups is much larger than the noise inside the group, the F value becomes large, and that gives stronger evidence that the group means are not all equal. But if the variation within the group is large and the group means are not very far apart, then we are observe the difference may simple and due to the chance. So the message of this slide is beautifully simple. ANOVA asks whether the signal between two groups are stronger than the noise within the groups. If yes, the difference is literally real and not statistical fluke. Next slide brings the full hypothesis testing process together into one connected flow. Instead of treating each concept separately, it shows how descriptive statistics, probability, and inferential decision making work as one engine. That is why this slide is such an important transition point. It helps learners see statistics not as an isolated formula but as a sequence that turns raw data into validated decisions. The process begins with extracting descriptive statistics. As the slide indicates, the first we calculate measure like mean and standard deviation from the sample. This gives a summary of what the data looks like before and formal testing begins. Next, we move into probability by translating those values into a Z probability distribution where the observed result is standardized into the Z score. A Z-score tells us how far the observed value lies from the expected mean in standard deviation units. And that lets us connect the observation to probability under a known distribution. Once the Z-score is obtained, we use it to derive a p-value. That p-value tells us how likely the observed result would be if the null hypothesis were true. Typically below 0.05, we reject the null hypothesis. If not, we fail to reject it. We do not do the math for its own sake. We use the engine of statistics to transform messy human data into decisions that are more confident, more defensible, and also more evidence-based. So let's see how to code with SQL. SQL follows a specific syntax consisting of keywords, clauses, and operators. We begin with data definition language or DDL to define the structure of the database. We use the create table command to build a brand new table with defined column names and data types. So here I'm using any online compiler. For now, I'm using Programmis. So here there are predefined columns as well. Let me just erase all those. So for creating a new table, the code will be create table followed by the name of the table. So let's say employees. And if you want to add the exact integer and also the heading, you just type in what the column names are. I'll give ID and space. You have to mention what kind of data will be initiated, which is int, suppose, and then comma followed by the next one, which is name, followed by again what kind of characters will be there. It should be var character, and let's give 255 and close the brackets. Next, if any other thing, let's add salary to it. Salary, what's the type? It will be int. So salary int. So salary, it will be an integer. Let's also add department ID. So department ID followed by the type, which is integer. Let's close this and run it. This will create a table with column names as ID, name, salary, and department ID, which has a specific values which is set. The name character will be absolutely a varchar, and then the ID will be integer, and salary again will be integer, and also department ID will be integer. So let's run this. So as you can see the output, the table employees already exists. So there's already a table called employees. So let's just change this name. So let's say employees table, and let's just run the code. As you can see, we have a SQL query successfully executed. However, obviously we are not printing any query as of now to show the table. Once the structure is defined, we moved on to a data manipulation language or DML. DML is used to manipulate the data stored in the database. We use the insert into command to add our new rows of the data into the table. Now, how do you add values into this table? So here the code will be insert into followed by the table name. I've given it as employees table. And then how do you add values here? So employees table, space values, and then you can add the value. So here the first one is that we have to enter is ID. So here you can see we have the employees table. So according to that, we can add it. So let's give the first value as one comma, where is employees table here? Then we have to give the name. So suppose the name is Ramesh, and then we have the salary. Let's say 30,000, and then followed by the department ID. Let the department ID be 10. So let's add the values. It's Ramesh and the salary will be 30K, and then followed by department ID, which is 10. So let's just close this up. And then if you want to enter any other values, just copy this, paste this here, and you can just change these values and you will have it. So just you can Control C, enter. And then here you can just change the numbers and name. Let's just change the department ID. Let's keep it 12 and run the sequence. So here's a small correction as well. The var character, which is the name that you have entered, it should be in single quotes. So that's the error. So let's just fix that and run the sequence. So here you can see SQL query successfully executed. However, the result is empty, so we are not going to print the table. To retrieve specific data from tables, we use the select command. We can write queries that domain a where clause to limit the output received based on a specific condition. We can also use order by clause to sort out the output in descending or an ascending order. So let's see an example of that. We are going to select name, salary, from which table? From employees. I've changed the name of the employees table to employees. Where? Again use caps in think. Where salary should be greater than 15,000. And then you can order by salary in descending order. So if you run this SQL code, employees, so the spelling here is wrong. So let's just run it after sorting that out. So as you can see, we have John Smith and Jane Dan, which is both are having 75 and 80,000, and it is having a descending order, which is 80,000 and 75,000. Often data has missing values. SQL provides single row functions that execute once for each row in a dataset. For example, the FVL function provides a mechanism to convert null values into more arithmetic-friendly data values, like converting a bank salary into 0. Now let's take an example of that. So again, we have to select name. So first, since that is already done, we have select name and we have FVL.
and enclose it by salary and make it into 0. And then from which table? Again, from employees. Close it up and run the SQL. So NVL is a pre-owned library of the install it. So whenever you're using the environment, make sure to install it. We can use aggregation function in select statements to produce meaningful reports. By using the group by clause, we divide the data into groups and calculate aggregated metrics such as an average salary per department. We can also exclude entire groups of data from our results by using the having clause. So let's see an example of that. So firstly, let's select department ID and also average of the salary. From which table? From employees. And then you can group by department ID having average salary greater than 50,000. So we have group, let's put that in caps since it is a code, group by department ID which is having salary more than average salary. Average salary greater than 50,000. So it should give me the department which is having an average salary of more than 50,000 rupees. So again, if I run this, you can see department ID 10 is having an average salary of 75,000. Department ID of 20 is having 80,000. In relational databases, data is naturally spread across multiple tables. We write the select statements and with join clause to access and combine data from more than one table, linking them together based on matching condition. So let's see how this works. First, we have select space e dot name and then space d dot department. And then we have from which table? From employees. Then we are joining these two back. So we have e dot join. Sorry, let's put that back. E dot join. Repeat. Department D on E department ID. So on the basis of departments, we are going to merge the department ID as well. So just let's run this. There is a syntax error. Let's just see. So basically, you can join two different tables based on one common column and then figure it out the rest. Finally, we use subqueries to solve more complex problems. A subquery is simple, a query nested inside another query. In this example, the subquery dynamically calculates the overall average salary and the main query uses that result to one retrieve employees who earn above that average. So let's see how that is done. So we have select name from which column? Which table? Employees, where salary, which is the column that we have given, is greater than select AVG average salary from, again, it's from the same table. So let's close it and run the SQL. So let me just close it and run the SQL. And here you can see the name is John Smith, which is having more than an average salary.
Now, if you come to the coding languages used in data science, there are two major ones that are used, which is Python and SQL. So let's introduce you to Python. Let's start with variables and string. String can be defined by single, double, or even triple quotes. Since Python strings are immutable, we cannot change the part of a string, but we can easily manipulate the output using built-in methods like lower to make everything in lowercase. So here I'm going to use Google Colab. You can use any other interface as required. And then if you want to initiate a string, we can just say my string and is equal to anything under double quote is considered a string. Hello data science. So I've given a string here. First, let me print this as it is. So here is the running code and let's say print. Just give the name of my string. So that's done. And here you can see it is hello data science. Now if you want to convert into lowercase, we can just add dot lower and then execute it. Now as you can see, the caps have changed to a normal lower class. There are so many inbuilt methods in Python. Make sure to use and explore everything one by one. In Python, data structures form a crust of the language. First, we have list defined by square brackets and then list which are mutable, meaning we can change the individual element after we create them. Next are tuples defined by parameters. Tuples are immutable, meaning they cannot be changed. Because they are locked in places, they process much faster than lists. Then we have dictionaries which are defined by curly braces, which hold unordered key value pairs. Finally, we have sets which are used to store unique, unordered elements. Now let's take a look at everything at one time. So first, let's start with creating a list. Let's say my list, which is 2, 4. List can be mutable, that means they can be changed, but when it comes to tuple, we cannot change. List can be changed, but the values in the tuple cannot be changed. So how do we assign a tuple? We have the name is equal to, instead of square braces, just circle braces and enter the value. Next, we have dictionary. So we have my dictionary where it can store a lot of different values. It doesn't actually have to be a string, it can be a number also. So just give it in curly braces, it works. So I can give name, and also I can give age. I can give number also, like 30. This also works. Now what about sets? Now again, it's the same procedure. Let's give a set also, which is equal to curly braces and then 1, 2, 3, 4. There is no single quote which will convert that to a dictionary. Now coming to conditional statements, which are used to execute code fragments based on a condition. The most commonly used construct is if else, which allows us to check if a condition, such as determining if a number is even or odd, or even execute the corresponding block of the code. So let's take an example of this. So here I'm just going to give a random number first to start off with. Then I'm going to start with a if condition. I'm checking if this number is even or odd. So if I divide this number with 2, the answer, if it is 0, that means if the remainder is 0, then let's print. What should we print? It is even. Now what else? Else print odd. Now make sure that if and else are in the same format or same space, and then shift enter. Now can you see it is already displaying that it is even. Now change the number to 7 and execute it again. You can see it is changed to odd. This is a simple if statement. Python also features looping construct for iteration. Like most languages, Python has a for loop, which is most widely used method iteration, allowing us seamless cycle through items in lists, tuples, or any other advanced data structures. So let's see an example of that. So a simplest example for that is for I. In, let's say, my list, I've already initiated the list, so I don't need to do it again. Print I. I'm just printing I until the condition or the for loop is executed. So let's enter this and it will show an error because I have also not initiated I. For I have missed out on in and shift enter. As you can see, 2, 4, it is printing the list. What is the list here? 2, 4, and it is printing the list here. So this again is the smallest example for a for loop used in Python. As you repeat, as your code grows, you will want to avoid repeating yourself. You can create functions to make reusable blocks of code. We will be using def keyword to define a function, pass a parameter, and return a compute result. For example, if you create a block on calculator or to calculate area, let's create it. def. Let's say the block is calculated area. Let's keep it small. And what are the parameters that I need to calculate the area, which is length and width. Now a function is ready. Now what happens inside of functions when you have the length and width? Let's return the value, which is the area, which is basically length into width. Now instead of writing the code again from scratch, whenever you want this, you can just call this function. Now the coding block is ready. Now how do you call this function? It's basically very easy. Just mention the calculated area, which is the function name which you have mentioned, and pass the parameters, which is the length. Let's say 10 and 5. The area should be 50. So just run it. So here I can see there's a spelling error. Let's find that. And so as you can see, we can get the answer as 50. Now, instead of writing the formula of length into width again and again, you can just give calculated area and your length and the width, and your answer will be there. Again, there is one more point. Instead of writing complex code from scratch, we import libraries. Libraries such as Pandas, which is one of the most useful data analysis libraries in Python and is essential for structured data operations. Using the read.csv function, we can instantly load a static CSV file into the data frame, which is similar to Excel workbook, and view the top rows with the head function. Now let's see how to import this. It's very easy. Import just the name pandas. Now if you have any CSV or Excel file, just you can upload it or import it from here itself. So what is the definition for that? We have df is equal to pd dot read CSV. If it is an Excel file, just replace the CSV with Excel and give the name, let's say train.csv. If it is Excel, again it will be .csv in single quotes, and this is done. This you're importing the entire CSV or even Excel file. Now it will throw an error because here in Google Colab we need to upload the file before executing any kind of read comment. And also if you want to get the first few of the headers or few of the values of that, just print df.head and you'll be able to get the first initial values of the Excel or CSV file. Real world data is messy, so we must perform data mugging. We use methods like isNull.sum to check the number if the null is missing values in each column. Most modules don't want to work with missing data, so identifying them in the first step before estimating and filling those values wisely. So suppose you already have a table and you want to find the null values or the empty values in the entire columns. So just df dot function and then just give sum so that it counts the number of null values in each column. So if you execute this, you will get a null values list as well. Python is considered one of the most widely used language. Why? Because it has inbuilt functions for everything you require. So make sure to explore every single part of it. This was just a basics of Python, but there is a lot more to it. Now let's talk about data preprocessing and exploratory data analysis from the bridge between the raw data and useful insights. In real world projects, data rarely comes in a clean and analysis ready format. It may contain missing values, duplicated records, inconsistent formats, errors, or even unnecessary noise. If this raw data is used directly, the results can become misleading. That is why preprocessing is the first important step. It provides the quality of a data set and makes it suitable for further analysis. Once the data has been cleaned, exploratory data analysis helps uncover the meaningful structure hidden inside it. EDA focuses on understanding distribution, spotting unusual values, identifying patterns, and also observing relationships between variables. This helps us understand what kind of data we have, what problems exist in it, and also what direction the analysis should take. Together, preprocessing and EDA helps separate useful signals from random noise. One prepares the data and the other helps interpret it. These steps creates a strong foundation for accurate modeling, reliable insights, and better decision making in the rest of the data science process. Data preprocessing and also exploratory data analysis do not happen in a straight line. They work as a continuous loop where each step improves the other. In practice, data scientists rarely clean the entire data set once and move forward permanently. Instead, they process the data, explore it, discover the issues or even patterns, and then return to cleaning and again with better understanding. Pre-processing focuses on removing noise and improving data quality. This includes handling missing values, correcting inconsistencies, removing duplicates, fixing formats, and even preparing variables for analysis. Once that is done, exploratory analysis begins to reveal the real structure of the data. It helps identify distribution, trends, and even unusual values and relationships between features. That exploration often exposes new problems that were not obvious at first, such as hidden outliers, skewed variables, and also categorical that need to be regrouped. Because of this, pre-processing and exploration feed into each other repeatedly. One pass through the data is often not enough. The data set becomes more reliable with each cycle, and only when the data stabilizes does it become a valid input for machine learning. This is why data science is described as iterative rather than linear. Data diagnoses are the first step to ensuring analytical quality. Before any modeling can happen, we must identify and resolve the common issue that prevents algorithms from functioning correctly or even lead to biased results. One of the most frequent problems is the presence of missing values or NANs. These represent incomplete records where data is missing entirely. They break statistical functions and algorithms, which generally require a complete set of inputs to perform calculations, making the identification and handling of missing data crucial first task. Another issue involves outliers, which are extreme values that fall far away from the rest of the data. For instance, if you have a dataset of human ages and one entry is recorded as 250, the outlier does not reflect a real biological possibility. Instead, it is an extreme deviation that mathematically skews averages and also variance, leading to an incorrect representation of the truth. Identifying these requires statistical checking or even visual inspection. Finally, there is the problem of dimensional imbalance. This occurs when features in the datasets are recorded or vastly different scales. For example, trying to compare an annual income of 50,000 with a value of 1.5 years of experience in mathematical problematic, as large scale will dominate the analysis. Addressing these issues through techniques like normalizations or scaling ensures fair mathematical comparison across all variables. Handling missing data is one of the most important decisions in pre-processing because it directly affects both quality and dataset size. Missing values, often represented as NAN, cannot simply be ignored. They must be first identified and then handled using method that fits the amount and also importance of the missing information. One option is to drop a missing data. This approach preserves the original truth of the available records because no artificial values are added. It is usually reasonable when the data loss is very small, such as less than 5%, or when the entire column is mostly empty and contributes very little. The trade off here is that dropping data reduces volume, which may weaken the dataset if too many records are removed. The second option is to impute, which means estimating and filling the missing values. This preserves dataset size but introduces a statistical assumption, so the method must be chosen carefully. For systematically numeric data, the mean is often used. For skewed numerical data, the median is more reliable because it is less affected by extreme values. For categorical data, the mode is commonly used since it fills the gap with the most frequent category. The right choice depends on how much the missing variable matters to the analysis. Dropping the data preserves pure truth but sacrifices volume. Imputing data preserves volume but introduces a statistical assumption. Choose the weight of the missing variable. Now, coming to outliers, outliers are values that lie far beyond the normal behavior of the data and need careful treatment because they can distort the result of analysis. A single extreme value can shift the mean, increase the variance, and create a misleading pattern that do not represent the majority of the dataset. That is why outlier treatment is an important pre-processing step. The first step is to define a threshold that separates normal observation from extreme ones. Once a value crossed that boundary, it is considered a candidate outlier. However, not every outlier is automatically an error. Some unusual values are caused by data entry problems such as recording age as 250, while others may represent rare but legitimate events. This is why domain knowledge is essential. A machine cannot always tell whether an anomaly is a mistake or a meaningful exception. After identifying the outlier, two common solutions are used. One approach is to trim it, which means deleting the record entirely. This is useful when value is clearly invalid. The other approach is to cap it, which means limiting it to maximum or minimum acceptable threshold instead of removing it. This keeps the record but reduces the mathematical impact. The correct choice depends on whether the extreme value is false data or an important but fair observation. Next, we have data transformation. Data transformation becomes necessary when features are recorded on different scale. If one variable is measured in very large numbers and other in very small numbers, algorithms may treat the larger scale feature as more important simply because of its size. Transformation fixes this by bringing feature into a comparable mathematical range. One of the common methods is min-max normalization. This technique maps raw values into fixed range, usually between 0 to 1. It is useful when algorithms requires hard boundaries when the data does not naturally follow a Gaussian or a bell-shaped distribution. The advantages is that every value is compressed into the same interval, which makes comparison easier across variables. However, min-max scaling is sensitive to outliers because extreme values can stretch the range and compress the rest of the data. The second method is Z-square or Z standardization. Instead of mapping values into fixed bounds, it centers the data around a mean of 0 and measures each value in units of standard deviation. This method is often preferred when the data contains outliers and that would distort min-max scaling. Standardization preserves the relative distance of values from the mean, and it's especially useful in models that assume centered or even normal distributed input. The choice between normalization and standardization depends on the data distribution and the algorithm being used. Now, coming to histograms, which is one of the major ways how data is represented. Histograms are one of the most powerful tools for visualizing the distribution and frequency of a single continuous variable. Instead of looking at individual data points, a histogram sorts all observation into discrete intervals or bins. The vertical axis then measures the raw count of increase that fall within each bin, creating a visual representation of how frequently different values occur. This shape is highly informative. It instantly reveals whether the data is skewed, meaning it leans heavily on one side, or whether it follows a symmetric pattern. It also identifies extreme trails where very few observations occur, which is often the point to the presence of outliers. Beyond just visualizing shape, histograms help inform technical decisions during the preprocessing. For example, the shape of the distribution dictates whether you should use the mean or the median to impute missing values. If the data is symmetric, the mean is often a good choice. If the data is skewed, the mean may be pulled towards the tail, making the median a much more accurate and robust estimate for filling in the gaps. By summarization, the entire distribution in one chart, histogram provides a quick, intuitive diagnostic that guides a cleaning process. Now let's get into another visualization tool, which is a box plot. A box plot is a standardized diagnostic tool that provides a 5-number summary of a dataset spread. The minimum, the first quartile, which is the Q1, the median, the third quartile, which is the Q3, and the maximum. This summary gives us an immediate snapshot of the data's central tendency and its variability without needing to look at every individual data point. The central part of the box plot, known as the box, represents the interquartile range, which covers the middle 50% of the data. This range is defined as the distance between the upper quartile, which is Q3, and the lower quartile, which is Q1. By visualizing this middle section, we can easily see how tightly or loosely the majority of the data is clustered around the median. Beyond the summary, the box plot provides an immediate visual threshold for outlier detection. By convention, any data points that fall more than 1.5 times of the IQR distance away from the edges of the box are flagged as potential outliers, represented in a plot as isolated circles. This makes the box plot an incredibly efficient diagnostic for identifying extremes. Furthermore, because it provides such a compact summary, it is a perfect tool for comparing data distributions across different categories side by side. Now let's talk about scatter plot. A scatter plot is used to visualize the relationship between two continuous variables. In this chart, each dot represents a single observation placed along two-dimensional axis where one variable appears in horizontal axis and the other in a vertical axis. In the example shown here, age is plotted against the estimated salary. So every point captures one combined observation of those two values. This type of plot is especially useful because it helps us see whether the two variables move together in a meaningful way. If the point follows an upward pattern, it suggests a positive relationship, meaning as one variable increases, the other trends to increase as well. If they slope downwards, it suggests a negative relationship. And if the points appear randomly scattered with no visible pattern, the relationship may be weak or simply noise. Scatterplot reveals covariance and correlation in a very intuitive form. They help answer an important analytical question: when feature X increases, does feature Y consistently rise, fall, or even remain unrelated? This makes scatterplot essential during exploratory data analysis because they allow us to quickly detect trends, spot unusual points, and even judge whether a relationship is strong enough to be useful for modeling. Preprocessing and exploratory data analysis are not optional steps, but the baseline for predictive truth. The visual moves from raw to refined to understand, which clearly shows the journey of data must go through before it becomes useful for machine learning. Raw data from the real world is usually noisy, incomplete, and also chaotic. It contains errors, irregulations, and also patterns that are not immediately ready for algorithms to interpret correctly. Here we understood that algorithms are mathematically blind. They assume that all the input data is the truth. That means if we feed messy or misleading data into a model, the model does not question it. It simply learns from it and builds patterns based on whatever it receives. That is why pre-processing of EDA are so critical. These steps translate chaotic real world events into signals that are valid, understandable, and structured enough for the machine to actually learn from it. Preprocessing removes noise, repairs gaps, and also aligns the data, while exploratory analysis helps us understand whether the patterns we see are meaningful. Only after this refinement can the data move from being raw information to becoming understood input that supports trustworthy prediction. Now let's actually see how data preprocessing happens in real world. So for this you need a data set. So you can go to Kaggle and search for whatever data set you require and download it and use that as a data set. So here I'm going with loan prediction. You can go with anything, that's fine. And you can just download anything. So I'll just go with this. So when you open a loan prediction copy of this, you will see notebook, input, output logs. Now, how do you actually download the data? You can go to input and here you can see view the data set. So open the view data set and here you will see an option of download. So just download this and you will get a loan data set.csv. So we can use this data set and run the code. Now again, for running the code, there are two ways any Python would work, any Python ecosystem would work. So either go with Jupyter Python, which is very efficient, and also here I am taking Google Colab since it's easy for me, and also it has Gemini integrated in it. So the first part is to upload the file here. So just go here, files. As of now, no file is created. As you can see, we can upload a file to it, upload the same dataset that we have downloaded, which is loan, and it will show you a warning, it's fine. Now, why I'm choosing Google Colab? Because it is an excellent cloud-based Jupyter Notebook environment for data science. Before running this script, make sure to download the loan prediction dataset from Kaggle or even upload the CSK file directly into the Google Colab file directly so that the read CSV command can locate it. So starting as usual for any Python program, we have to import the required libraries. So import the required libraries. What are the required libraries I would require here? Sorry. Here I would be requiring pandas. So import pandas as PD. And then what are the other things? NumPy also is required. Import NumPy as NP. And also for visualization, as it's suggesting, we have import matplotlib.plot as plt. Now I think these are the basic imported libraries that is required. The next step is to load the dataset that we have uploaded here. Now how are you going to do that? Let's see. So the second step is to load the dataset. And how are we going to do that? With the help of the pandas. Make sure that the file which has to be loaded is already uploaded in Colab. So here for uploading, we need df is equal to pd dot read, and which kind of file. It is a CSV file here. If it is Excel, go with Excel, and the name of the data, which is loan data dot CSV, and close the columns, and that's it. You can load your data. Now, how do you actually see if it's loaded? Just type in df dot head and semicolon, and there you go. It is printed. This is the data that we are having, which includes loan ID, gender, married or not, dependents, educational, self-employment, and loan status. Loan status is at the last, whether yes or no. Now, after uploading the data, what is the next step? Second is we'll do a basic EDA, which is exploratory data analysis. So this is the above things are very basic. So let's add a text. Here it is EDA basics, very basics. So the first step in EDA basics is to generate a statistical summary of all numerical columns. So we should have an idea of all the numerical columns, whether which is the highest, which is the lowest, what is the mean, median, standard deviation, minimum, quartiles, and also maximum. So how do you do that? It's very simple. You have only one statement to print, which is df dot describe. If you run this, you can see here we have count, mean, standard deviation, minimum 25%, which is Q1. We have Q3 and maximum value of the columns, which are numerical data sets. So you can see here income of a person count is, we have around 6,14,000, 6,014,000, and then the average mean is 5,403, standard deviation is 6,109, minimum is 150, maximum is 3,000, sorry, maximum is 81,000, and we have co-applicant income also, loan amount, whatever the loan amount is taken, we have an mean value of 146.412162. So we'll get an idea of what kind of numbers are there, what is the maximum minimum of each column, etc. Now after this is visualizing, which is distribution and outliers. We have to identify the outliers in order to start it. For that, first we are going to plot histogram. Let's say we are plotting a histogram with 50 pins to view the distribution of applicant income. So as you can see, we have applicant income. So let's plot a histogram against this number. So for that, df call the column name. What is the column name? Applicant income without any gap. Dot HIS, which represents histogram, and bin let's give 50, and just run this. There's an error. Let's take a look at it. Sorry, this is histogram, so HIST, and just run it now. As you can see, we have the histogram ready. So as you can see, the income mostly ranges between 0 to 20,000 range here, and many people's range from 0 to 10,000 as well. Very few are there above 30,000, here and there dots. So we can identify the outliers. You can consider these as the outliers and concentrate on this graph, which is majority of the people. Now, what if I have to give a name for this histogram? So just plt.title and give the title name. Let's say distribution of applicants' income. And in some cases, the graph may not come. So for that, just you need to add one more statement, which is plt.show. Here it's coming, but usually in Jupyter Notebook, you need to add the command for the graph to appear. So when you execute this, as you can see, the title is already added, which is distribution of applicants' income. Now let's go with the box plot. Now here let's plot a box plot to visually identify extreme values or outliers in the income data. Now we want to spot the outliers in the income data, which is, let's go up and check income. So applicant's income, this is the section that we are going to see for a outlier. So let's start. Again, it's box plot. So we have df dot box plot, and we have column is equal to applicant's income. Make sure the name of the column is similar, or obviously it should be the same. And again, let's give a title to it. So plt dot title box plot of applicants income. Close it, and again, if there is no graph appearing, just add plt.show. Let's execute this, and as you can see, there is one outlier in 8,000, another one between 6,000, 5,000. Also it is an outlier, and most of them belongs to 10 to 20,000. So I can consider at least these three as an outlier. So you can either remove these values, clean these values, etc. Now let's check, that is the next part. So next part is called data mugging, which is cleaning the missing values. First, you need to check the exact number of missing values, which is the null values in every single column. So for that, there is a statement which is df.isNull.sum. So execute this, and here you can see what are the empty spaces in the entire data set. So we have 13 gender, in the gender column, 13 of the values are null, which is empty. In the married section, we have 3, dependents we have 15, self-employed we have 32, loan amount we have 22, and credit history we have 50 of them missing. Now we know that if we have an outlier, we can either remove it or replace it with mean, median, or mode depending on the type of data. Similarly, if there is missing value, depending on the column which is more important to the loan status, you can identify that and see if you can replace it with mean, median, mode, or if the column is not that really informative, you can go and remove it off. Now, the second option is to fill in, which is impute. So let's say loan amount, we have 22 of them missing, right? So let's fill it up with either mean, medium, or mode. For here is, since it is amount, I feel mean would be more appropriate for it. So how do you fill those values? We have df, again column name. Which column do we want to fill? Loan amount. There is no space, so we are not going to give space. Now fill NA, which is NA in values, with df dot, we have to calculate the mean, right? So call the column, loan amount dot mean of the entire column, and close it, and also keep the in place as true. So let's execute this. There's some error. Let's take a look. Your name true is not defined. The T should be capital, and then run it. So I think it has done the job. So as you can see, before loan amount was 22 of the null values. Now let's see how many are remaining. It should be 0. Let's see. So as you can see, loan amount, everything was replaced by the mean of the column. Similarly, for every column, there should be 0 null values and 0 outliers for more precise machine learning models. The next step is data transformation, which is to apply a mathematical log transformation to the loan amount to nullify the effect of extreme outliers. Now here's how you deal with actual outliers. So again, I'm going to consider loan amount itself. So for that, in a mathematical way, we are going to take the log of the same column. So let's say df and loan amount log value, right? So let's name it log. This is a new column that I'm creating, which will be equal to np dot log of the column. What is the column? This is the column. Now this calculates the log of the entire column. Now let's just run this, and it's done. Now it normalizes everything. Not too many outliers will be there. It will be between a certain amount, and it will be like ratio kind of a format. Now let's plot a new histogram to verify that the transformed data now resembles a normal distribution. Now we have already taken a histogram. So let's do the same for the loan amount. Sorry, it's not loan amount, it's loan amount log. This is the new column, right? So let's replace it, and let's say normalization. It should be equal to the Gaussian that we just talked about. Normalizing data. And let's run it. So as you can see, it has a wave to it. It is a normalized data. Let's change the number of bins and see the results also. So as you can see, it is resembling a Gaussian representation, which is equal to a good data values. Now this is all about data preprocessing and EDA. Please check out other data sets, work with that, play with them, and understand your data before even going to the next step, which is modeling. Try to replace your none values and also outliers with mean, medium, mode, whichever suits the best. Now, regarding correlation graphs, one of the most important parts of knowing if the column is actually valid or not, you can plot a correlation graph. Now, how do you plot a correlation graph? It is very simple. You just need to do df.corr. df is the data set that we have loaded in. So I'm just going to get the correlation. So just type in and execute it. There's an error. Let's see what the error is. Since Colab also has Gemini, it's easy for us to identify the errors and validate it, and also it will get it corrected itself. Okay, so it's showing me to use this, and there is an option of accept and run. So just accept and run. As you can see, there is a correlation. So you have to consider for log amount, credit history. So before that, I forgot to tell you one more thing. We have categorical data, right, in the data set. Suppose here we have yes, no, yes, no. This should be replaced by ones or zeros depending on whichever suits you. And then here you will get the correlation of that as well. So you can see which table is actually useful. And then there is another option called heat map. For that, let's just import Seaborn, since that is the library that is having this heat map. And then we have data, which is df, and then a not true and vigorous. So let's just enter it. There's again an error in it, and let's just ask Gemini to help us. So as you can see, we have column name and the numbers here. It's a little bit scattered. Maybe we can reduce the range or something. So the colors are mostly violet, so it is between 0 to 10,000 itself maximum. So like this, you keep on analyzing your entire data set. You will have an idea of which column is important and which is not. So for the columns where this is not important, you can either drop the entire column, or just the null values, you can drop it down. If the column is very important, just replace the null values with either mean, median, mode, depending on the exact numbers that you want, or you can replace it with whichever number you are comfortable with according to the data that you are pre-processing it. Welcome to this module on machine learning and predictive modeling. As the subtitle says, this module is about paradigms, processes, and also core algorithms, which means we are now moving from data preparation to the stages where machines begin to learn patterns from data and even use those patterns to make predictions. In the previous module, we focused on preparing data properly through preprocessing and exploratory analysis. That step was essential because machine learning does not start with algorithms alone. It starts with clean structure and meaningful input. Now in this module, we will build the foundation and ask a few new questions. Once the data is ready, how can machine use it to identify relationships, detect patterns, and even predict the future outcomes? This is exactly what machine learning is designed to do. It gives systems the ability to learn from examples rather than being explicitly programmed for every possible rule. Predictive modeling then takes that learning and applies it to all further or unseen data. So in this module, we will explore the major learning paradigms, understanding how models are trained, and look at core algorithms that power modern intelligence systems. The next step is to clearly define what machine learning is actually and why it matters. So let's get started. Now we'll talk about the basic taxonomy of machine learning by dividing the field into three major paradigms, which is supervised learning, unsupervised learning, and reinforcement learning. This classification is very important because before we study algorithms, we need to understand the kind of learning problem we are trying to solve. Different machine learning methods are designed for different data types, objectives, and also feedback mechanism, and this slide gives you a high level map. The first category is supervised learning, which defines as learning from labeled data. In this paradigm, the model is given input data along with the correct output, so it learns a mapping between features and target values. This is commonly used for a task like classification and regression, where the goal is to predict a known label or number of new data. The second category is unsupervised learning, which focuses on discovering hidden patterns. Here, the data has no labels, so the model explores structure on its own, often through clustering, grouping, or even dimensionality reduction. The third category is reinforcement learning, which is like a reward based trial and error. In this approach, an agent learns by interacting with the environment and improving its behavior based on rewards and penalties. So, this slide gives us a full landscape, and the next step is usually to begin with supervised learning since it is important to direct and widely used starting point in predictive modeling. Let's take a brief look at what is the difference between supervised learning and unsupervised learning. This will help us understand how these two paradigms differ from each of data, goal, algorithm, focus, and real world use. While both belong to machine learning, they solve very different problems. Understanding this distinction is essential because choosing the wrong learning type can lead to a wrong modeling approach altogether. On the left is supervised learning, which is described as method based on labeled data, where inputs are mapped to no outputs. Its core goal is to predict a specific target variable, and its main algorithmic focuses on classification and regression. The example on the other side is predicting a coin currency based its specific weight, which is clear feature to label mapping. This means the model learns from examples where the answers is already known, then applies that learned relationship to a new case. Next, we have unsupervised learning, which works with unlabeled data, meaning there is no predefined output. Its goal is to discover underlying structures and groupings, and the main algorithmic focus is clustering and association. The example given is grouping cricket players into batsmen and bowlers based on patterns in runs and wickets without prior labels. So the key difference is simple. Supervised learning predicts known outcomes while unsupervised learning discovers hidden structure. Now let's talk about one of the most important ideas in machine learning, which is the train test split. We should never mix training and test data because a model must be evaluated on unseen data to prove that it has actually learned patterns, not just memorized the examples it gives. The distinction is critical because the true goal of machine learning is generalization, which means performing well on new data, not just on historical records used during training. Usually, the standard split is 80 to 20 split pipeline is considered, where historical data is divided into two parts: the training set, which is 80% of the data, which is used to establish the mathematical rules of the model. In other words, this is the portions where the algorithm studies patterns, relationships, and also structures in order to build a predictive function. The testing set, which is remaining 20%, is kept separate and used later to verify accuracy on unseen data. This gives us more honest measures of performance because the model has never seen those examples before. So the key takeaway is simple. Training teaches the model, but testing validates whether the learning is real. The next question that would arise would be, why do we need to split the data at all? The reason is written clear. If a machine sees the test data during training, it begins to memorize the noise instead of learning the underlying signal. That is one of the biggest dangers in machine learning because a model may appear highly accurate during the development while actually being weak on new real world data. The first one is memorization, also called as overfitting. In this case, model learns the tiny fluctuations, irregular jumps, and random noise in the training data instead of true pattern. That is why the slide repeat. An overfit model performs very well on the data it has already seen, but poorly performs on unseen data because it has not captured the general structure. The next problem would be generalization, which is the correct objective. Here, the model captures the smooth underlying pattern instead of just chasing every random point. That is why it is a right fit which is robust and pattern based. So that the purpose of the split is not just technical separation, it is safeguard that helps us tell the difference between a model that truly understands the data and one that has only memorized it. Now let's talk about the idea that regression forms the mathematical bedrock of predictive modeling. In other words, before we study many advanced machine learning methods, we first need to understand regression because it provides one of the most fundamental ways a model learns relationship from the data. Now there are two core forms, one is linear and logistic, which represents two essential predictive approaches. Linear regression is used when the output we want to predict is continuous, such as salary, sales, temperature, or even price. Its goal is to find a mathematical relationship between input variables and a numerical outcome, usually by fitting a line that best represents the trend in the data. This makes it one of the simplest and most interpretable predictive models. It helps us understand how changes in one or more feature influence a continuous result. Logistic regression, despite its name, is used for classification problem rather than continuous prediction. It is typically applied when the output belongs to categories such as yes or no, spam or not, pass or fail, etc. Now let's dive into linear regression, one of the most fundamental algorithms in machine learning and predictive modeling. Linear regression finds the straight line that best fits the relationship between the variables in order to predict a numerical output. That makes it especially useful when the target we want to predict is continuous, such as price, temperature, demand, or even income. The equation shown on the slide, which is y is equal to b0 plus b1x, or y is equal to mx plus c. Now, this represents the straight line relationship. Here, x is the input variable, y is predicted output. The slope determines how much the value of y is. Y changes when x changes, and the intercept shows where the line begins. The visual on the right also highlights residual, which are vertical gaps between the actual data points and the regression line. The goal of the model here is to minimize these residuals so that the line represents the overall pattern as accurately as possible. Now, some of the use cases include forecasting stock prices, predicting temperatures, or even estimating a diamond's price based on carat weight. These examples show why linear regression is so important. It transfers patterns in historical data into numeric prediction for unseen cases. Once we understand linear regression, the next logical step is to move to logistic regression when predictions shift from numbers to categories. Now let's dive deep into logistic regression, which is used when a goal is not just to predict a continuous number, but to decide which category an input belongs to. Logistic regression predicts the probability that an input belongs to a primary class and then uses a threshold to convert that probability into a strict category. That is why it is widely used for binary classification problems. The key here is mechanism behind logistic regression is sigmoid function shown as in the graph on the right. The S-shaped curve maps any input a value between 0 to 1, which can be interpreted as probability. The dashed line at zero point 0.5 in the diagram represents the decision boundary or threshold, meaning the values above that point may be classified as class A, while the values below it may be classified as class B. This is how a model turns probability into a final decision. Some of the use cases are spam versus not spam, whether it's a cat versus dog, etc. In each of these examples, the answer is not a number but category. So logistic regression becomes a natural choice. Now let's have a direct comparison between linear regression and logistic regression, helping learners clearly understand when to use each one. Here on the linear regression side, the output type is continuous, meaning it's a model predicts numbers. Its visual shape is a straight line, and the mathematical goal is best fit, usually by minimizing mean squared error. That is why the practical question of linear regression is how much or how many. This makes it suitable for tasks like predicting salary, house price, temperature, or even sales. On the logistic regression side, the output type is categorical, usually binary class labels. Its visual shape is a S-curved or sigmoid, and the mathematical goal is estimate probability and then apply the same threshold between 0 and 1. That is why the practical question here becomes which category or yes or no. So the type of algorithms which you want to choose depends on the type of answers that you actually want from machine learning. Algorithm's choice is dictated entirely by shape of the target data. In simple terms, the kind of output you need to predict determines which algorithm is appropriate. First, let's take a recap of what the data pre-processing looks like, and then we'll move on to the machine learning algorithms. So as we all know, I've imported all the necessary libraries here. Then we have read the data, installed the data, and we have calculated the null numbers in each of the columns. So as you can see, we have gender, married, and 15 people. Columns are there which are having null values. Now here for loan ID, since this is irrelevant data, loan ID doesn't gives us any useful information. So I'm going to drop that entire column. Next, to replace the null values in gender, I'm going to replace it with the most repeated one, which is the mode value of the entire column. For married, I'm going to again replace it with the most repetitive values. For dependents, again going to consider mode. Self-employed, again mode is replaced. Credit history is also by mode. I've used everything as mode. Here even the loan amount term is replaced by the mode. Coming down here, if you look at loan amount, I'm not going with the mode because we cannot consider it as the mode value since each will have a different value. Here I'm filling it with the mean value, which is the average. Then we come here, we are going to remove the outliers, which is away from the natural data. I have calculated the numeric DF, Q1, Q3, IQR, and then here as you can see, I am replacing the outlier condition as well. So we have a clean data. Next, we are using square root transformation to normalize the distribution. Now, what is normalization of the distribution is basically converting huge amount of numbers into minimum value, which will be in pointwise. So even if the numbers are in lakhs, we'll get it in points. So it's easier for us to compare the values. So here I have used square root transformation. We can use any other model, or we have transformers as well. You can just fit the model and it will give you a normalized table. Next, here I've shown you how to convert the categorical data into the numeric format. As you can see, we have education, self-employed, applicant, sorry, not applicant, but we have property area and loan status as categorical data, which is a group which is, suppose consider education, we have graduate or not graduate. When it is self-employed, it is yes or no. When it is loan status, yes or no. Property area is urban or rural, etc. There are maximum 2 to 3 values. Now how do you convert these values into numerical format? Either we can go with fitting a model, or you can do that manually. Manually will take a lot of time. So what I've done is I've considered ordinal encoder, where it converts the categorical into the numerical as zeros and ones. So here you can see all the 6 of the columns are here, and this is the code where select the column encoder dot fit transform df is equal to the column name, and then we before that we have to have scikit-learn and then import the ordinal encoder and then give the encoder as ordinal encoder in brackets. Now if you run this, these values which we earlier saw as categorical value will be converted into numerical value. There you go. Gender as zeros and ones, and education is zeros and ones, self-employed as zeros and one, and finally the loan status as zeros and ones. So this is a normal cleaning and getting our data ready for our next step. Now next step is to define our independent variables, which is x, and dependent target, which is labeled as y. Now here let's consider a minimum amount. Let's consider only 3 column as x, which is the input. So we have x is equal to df. What are the columns that we are going to consider? Let's consider most important one, which is income, applicant, income, and then the next, I think it's loan amount log. I think I don't have the loan amount log, but I have loan amount. So I'll use loan amount, or else you can just go ahead and just calculate the log amount also, that's fine. And then let's consider credit history. Credit history, and this will be your X. So let's just run it. And now we need, sorry, let's just run it. And now we need there's an error. Okay, I think spelling error or something like that. Okay, here I've left a gap. Let's cover that up, and that's fine. Now we have to know our target variables. Now what is our target variable? You all know that it is status, loan status. So we'll just give y is equal to df and loan status and shift enter, and it will be running. Now we have our x and y values. Okay. So the next important step is to test train split the entire data, that which is x and y data. So for that, firstly we have to install the library which is required, which I have already done, which is from sklearn.model selection import train test split. Now after giving this, it's time to split the entire data in 80:20 ratio. Now we have x train, we need to divide it into 4 parts: x train, x test, y train and y test. So let's say x train, x test, and then we have y train and y test is equal to train test, give the x and y values, x comma y comma. Here you have to mention the test size. Here the test size will be 0.20, which is equal to 80:20 ka split. Test size will be equal to 0.20. If it is 70:30, it will be 0.30. After the test size, we need to give a random state. We cannot pick which data will go into the x train, x test. It's a random state. So let's give a random state. Let's say 42, that's fine. And let's run it. So it's done. Our data is separated 80% and 20%. Let's just calculate the length of x train and see. So length of x train, we have 142. Now what is the length of x test? As you can see, it is 36, which is 20% of the data. Now the next part is training the model. Now which kind of model? Is it logistic or is it linear? Firstly, we all know that the categorical data that we are having as y, so we are going to prefer logistic regression. If it was numerical, we would have preferred it to linear regression model. Okay, now how do we fit this model to a linear regression or logistic regression? As per this data, logistic regression is the right way to go by. So before that, we need to again have a library of logistic regression. So as you can see, I've already installed from sklearn.linear model import logistic regression is the thing. And then let's fit this model to the test train split that we have created. So first we have model is equal to logistic regression. And then now we are training the model using the dot fit function. Now how do you fit the model? Here we have model, which is the logistic model which we have given. Dot fit, we have first x train. We are just training the model with x train and y train, comma y train, which is 80% of the data. Now let's execute this. There's an error. Let's see what that is. So here I've given model as logistic regression and then fit the data. So as you can see, the error was basically I had converted the entire loan status into one categorical value. I changed that up to zeros and ones depending on yes or no values. Now the next step is to just make predictions and evaluating, which is confusion matrix. So for that we need specific type of libraries from sklearn. So we have from sklearn metrics, import, accuracy, score, and also confusion matrix. Now let's just run it, and it's already there. Now we'll ask the train model to predict the outcomes for the rest of the 20% unseen test data. Those are predictions basically. So for that, let's just clear this. Okay, anyways, leave it. So for that, it is predictions is equal to model. We are fitting the model again, dot predict, and then we are giving the x test. These were kept aside so that we can test the data. So again, if you press enter, it's done. Now let's calculate and print the accuracy score. Now we are comparing the actual y to the y predict. So we have accuracy is equal to accuracy score in terms of y test and prediction. So if you type in enter, there is a small error, prediction does not exist. So this is predictions. Now the value here is, let's just print accuracy, print accuracy. Here the accuracy is 0.8%. That means we have predicted 80% of the y test data towards the predicted y test values of the machine learning generated outputs. Now at the last step, we are going to print the confusion matrix. Now how do you actually put the confusion matrix? It's confusion. Let's print it first. We have confusion matrix. We are placing it against y test and prediction. Now if you print this, we have 18 is to 33 and 4 is to 130. So here this grid represents the true positives, true negatives, false positives and false negative. So our accuracy is pretty much good enough. 80% is good enough accuracy to proceed with the model. Let's start with the fifth module, which is data visualization and communication. At its core, data visualization and communications are about translating mathematical complexity into human clarity. Data by itself can often feel overwhelming. Large spreadsheets, calculation metrics, and raw numbers may contain valuable insight, but if people cannot understand them easily, the information becomes difficult to use effectively. This is where visualization becomes so powerful. Human beings naturally process visuals much faster than raw numeric data. We recognize patterns, trends, comparisons, and changes more quickly, even though charts and visuals, than through row of numbers. A good visualization helps simply complex information so people can understand what's happening without spending too much time analyzing the data manually. But creating charts alone is not enough. Communication is equally important. The purpose of visualization is not just to display data, but to explain the meaning. A chart should help the audience understand what matters, why it matters, and what actions or insights should come from it. If a visualization looks effective but creates confusion, then communication has failed. This is because especially important in real world environments where people from different backgrounds work with data. Business leaders, managers, analysts, and clients may all look at the same information differently. Effective communications help bridge that gap by making technical insights easier for everyone to understand. In many ways, data visualization is the form of storytelling. It turns abstract numbers into something meaningful, memorable, and actionable. When done correctly, it helps people much faster and more confident decision using the data. One of the most important ideas is data work is understanding that data is useless in its raw form unless it can actually drive business actions. Collecting data alone does not create value. Organizations capture massive amounts of information every day, but the real impact comes from how the information is transformed into understanding and decision making. The data lifecycle usually moves through several stages. First, the data is captured from different sources. Then it is maintained and stored properly so it remains reliable and accessible. After that, the data is processed and prepared for analysis. Once the analysis is completed, insights begin to emerge. But even after all that work, there is still one critical step left, which is communication. This stage is often called the final mile. It's the point where technical analysis must be translated into something people can understand and act upon. If insights remain inside notebooks, dashboards, or technical reports that nobody understands, then the work loses much of its value. A data professional is not only expected to analyze information accurately, but also to explain findings clearly. Stakeholders, managers, and decision makers may not have technical background, so communication becomes the bridge between analysis and action. The ability to simplify complex insights into clear narratives is what makes data truly useful in the real world. This is why communication is considered such an essential skill in analytics and business intelligence. The success of the project is not just measured by only one quality of analysis, but also by whether people understand the results as well enough to make informed decisions from them. Good data visualization is not just about making charts look attractive, it's about making information easier to understand accurately and quickly. Strong visual communication follows a few important design standards that help reduce confusion and improve clarity. The first standard is readability. A chart should be easily to interpret without unnecessary distraction. This is where the idea of maximizing the data to ink ratio becomes important. In simple terms, most of the visual space should focus on the actual data, not the decorative elements. Too many borders, shadow colors, labels, or even extra graphics create chart junk, which makes the audience work harder to understand the message. Clean and simple visuals actually make communication much more effective than overloaded designs. Second is standard clarity. Visualization should represent data accurately and maintain correct mathematical proportions. If scales are manipulated or values are displayed inconsistently, viewers may misunderstand the information completely. Even small design mistakes can change how people interpret trends, growth, or even comparisons. A good visualization helps the audience trust the data because the presentation remains precise and honest. The third is being unambiguous. The audience should not struggle to figure out what is the chart trying to communicate. This is why unnecessary 3D layouts, distorted perspectives, and unusual visual effects are often discouraged in professional reporting. While they may look visually interesting, they can distort perceptions and also make values harder to compare accurately. Ultimately, the purpose of design in data visualization is not decoration, it is communication. Every design choice should help the audience focus on the insight instead of struggling to decode the visual itself. Clean, accurate, and straightforward visuals almost always lead to better understanding and better decisions. One of the biggest goals in data visualization is eradicating ambiguity. A viewer should never struggle to understand what the data is saying. If a chart creates confusion, focus extra interpretation, or distorts value, then the visualization is no longer helping communication. A common example of ambiguity comes from using exclusive visual effect like 3D charts. While these charts may appear visually impressive at first, they often make comparison much harder. Depths, angles, and perspective can distort the actual values being presented. A bar is placed in the background may appear a smaller simply because of the perspective, not because of the data itself is smaller. This creates unnecessary cognitive effort for the audience. In contrast, simple 2D charts are usually much more effective because they prioritize clarity over decoration. When bars shares align baseline, viewers can compare values quickly and accurately. The human eye naturally interprets length more effectively when everything begins from the same reference point. This is why professional dashboards and reports typically avoid unnecessary visual complexity. Direct labeling also improves understanding. Labels placed close to the data reduces confusion and speeds up interpretation. Small design improvements like this can make a huge difference in how quickly information is understood. The broader lesson here is good visualization removes obstacles between the audience and the insight. Every unnecessary effect, distortions, or even decorative feature increases the chance of misunderstanding. Simplicity is not about making visuals boring, it's about making communication precise, effective, and also trustworthy. In professional environments, people rely on charts to make decisions. That's why clarity and accuracy should always matter more than a visual decoration. Effective data visualization always begins with purpose. Before seeing any chart or visual, it's important to clearly define the precise analytical intent of the data. In other words, we first need to understand what questions we are trying to answer. Without that clarity, it becomes very easy to choose visuals that look good but fail to communicate the right insight. Different analytical goals require different visualization approach. One of the common goal is comparison. Here the objective is to evaluate the difference between categories, values, or even groups. For example, comparing sales across regions or performance across teams. In these situations, visuals that emphasize length and align baseline usually work best because they make difference easier to interpret. Another important goal is understanding relationships. Sometimes we want to know whether two variables are connected in some way, or does customer satisfaction improve retention. Relationship based visuals help identify correlation clusters and trends between variables that may not be obvious in raw data. We also visualize to explain proportions. This focus on showing how individual parts contribute to a whole market share, budget allocation, or even population distributions are common examples. The audience is not just comparing values independently, they are trying to understand the composition and contribution within a total. Finally, some visualizations are designed to reveal patterns. These help us uncover trends, cycles, spikes, anomalies, or even changes over time. Pattern focused visuals are especially useful in forecasting, monitoring, and decision making because they help people recognize behavior that may otherwise remain hidden. The important idea is that forms follows function. The chart type should always support the analytical purpose of the data rather than being chosen purely for appearance. An important skill in data visualization is knowing the difference between comparisons and proportions. Even though both involve numeric data, they answer completely different analytical questions and each require a different visual approach. Comparison are used when a goal is to identify the difference between entities. For example, comparing revenue by region, sales by product category, or even performance across departments. In these cases, the audience want to quickly understand which value are higher, lower, or even closer together. Visuals designed for comparisons work best when they use shared baselines and variable length. This is why bar charts are so effective. The aligned starting point allows human eye to compare values accurately and quickly. Proportions focus on something different. Instead of comparing independent categories, they reveal parts of a whole. A common example is market share, where each segment contributes to total percentage. Here, the audience is trying to understand compensations rather than ranking alone. The relationship between the parts becomes more important because every segment contributes to the complete whole. This distinction matters because using the wrong chart can weaken communication. If the goal is comparison, proportion focused visuals may hide important difference between values. On the other hand, if the goal is to explain composition, a simple comparison chart may fail to show how the total is distributed. Good visualization starts by understanding the analytical intent behind the data, that we are trying to compare categories or are we trying to explain how something is divided. Once that question is answered, clearly choosing the right visualization becomes much easier and far more effective. Another important distinction is data visualization is understanding the difference between relationships and also patterns. While both help us explore data more deeply, they focus on different types of analytical insights. Relationships are used to show dependencies between variables. The goal here is to understand whether changes is one of the variable are connected to the changes of others. For example, we may want to study the relationship between age and income, advertisement speed and sales, or even study hours and exam performance. In these situations, the visualization helps reveal whether variables move together, move independently, or show some form of correlation. Charts designed for relationship usually focus on plotting multiple data points across coordinate systems. This allows viewers to observe direction, strength, and clustering with the data. Sometimes the relationship may appear strongly positive, sometimes negative, and sometimes there may not be any meaningful relationship at all. These visuals are especially useful in analytics because they help us uncover hidden connections that are difficult to notice in raw tables of the numbers. On the other hand, patterns focus on something slightly different. Instead of studying dependency between variables, pattern based visualizations help us understand frequency and distribution with the data itself. They reveal the overall shape of the data and help spread peaks, gaps, and even unusual behavior. Histogram and density plots are commonly used for this purpose because they help display how values are distributed. This becomes extremely useful when identifying trends, detecting anomalies, or also understanding whether the data follows accepted behavior. In many real world situations, recognizing patterns is essential before building models or making business decisions. The important idea is that relationship helps explain connections between variables while pattern help explain the structure and distribution of the data itself. As organization grow, the way they communicate data also becomes more structured. Different business situations require different level of detail, speed, decision making, and support. This is why visual reporting is commonly scaled across reports, scoreboards, and dashboards, with each of them serving a different purpose. Reports are designed for deep context and detail. They are usually sequential, meaning information is presented step by step in a structured flow. Reports are best suited for comprehensive and historical analysis where users need explanation, breakdowns, trends, and also supporting information. They are often used by analytics managers and leaders and leadership teams when detailed understanding is more important than speed. Scorecards focus primarily on KPI tracking. Their purpose is to measure performance against goals and targets. Unlike reports, scorecards are more performance oriented and structured from a top down perspective. They commonly combine lagging indicators while measure post results with leading indicators, which helps predict future performance. This allows organizations to monitor whether they are moving in the right direction strategically. Dashboards are designed differently. Their primary goal is high level orchestration and immediate operational insights. Dashboards are usually more constrained because they prioritize speed, visibility, and quick interception. Instead of deep analysis, dashboards help us monitor current conditions, identify issues quickly, and support fast decision making in day to day operations. Understanding the difference between these formats is important because each serves a unique business need. Report provides depth and scorecard provides performance measurement and dashboard provide rapid operational awareness. Choosing the right reporting medium help organization communicate insights more effective and support better decision making at every level. One of the biggest challenges in dashboard design is managing cognitive load. When users are presented with too many charts, matrices, and visual elements at the same time, the dashboard becomes difficult to interpret. Instead of helping decision making, it creates confusion and slows the understanding. This is where the dashboard rule of 7 becomes important. The idea behind this rule is that the dashboard should contain a maximum of around 7 major visual objects or focus areas. Human attention is limited and people can only process a certain amount of information effectively at one time. When too many elements compete for attention, users struggle to identify what matters most. A good dashboard creates hierarchy. The most critical lagging indicators should appear on the top because they usually represent the most important business outcomes. This placement naturally guides users' attention towards the highest priority information first. Supporting visuals and operational details can then be organized into separate zones below. Another important principle is consistency. Each zone should use purpose driven chart selection based on the type of insights being communicated. Trends are easy to understand through line charts, bar charts, and also summary metrics through KPI indicators. When visuals are chosen internationally, users can interpret information faster with less mental effort. Dashboard should also separate information logically instead of placing everything together randomly. Organizing matrices into clear sections improves readability and helps users navigate information more naturally. An effective dashboard is not just the one with most data. It is the one that communicates the right information quickly, clearly, and without overwhelming the audience. Simplicity, hierarchy, and focus design are what makes the dashboard useful in real world businesses environment.
This is module 4 demo. In module 4, our model generated a raw text based confusion matrix. Handling a raw grid of numbers to a business executive usually causes confusion. Today, we are going to translate those mathematical complexities into professional, easy to read, executive visual using Seaborn. Now, the first step is to visualize the confusion matrix as heat map. So, let's just see if heat map is already there. Seaborn is already there, so I don't need to import it again. So if not, just import the Seaborn. Seaborn is a powerful Python data visualization library built on top of Matplot that makes graphics look higher professional for business stakeholders. Next, we'll import the Matplotlib, which is this one. Now, this is to control the size and display of our visual figures. Next, from Skikit-learn, we need to import the metrics import. So let's do that. So here we can import the Skikit-learn. So from sklearn, import confusion matrix. and let's just run it. And it's imported. Now, why do we import this confusion matrix? We use it because function to evaluate where our classification model made correct predictions versus errors is identified using this. Now, let's just import that. We have CM, which is equal to confusion matrix, and then give your y test and predictions. And let's just run it. We calculated the confusion matrix by comparing the actual holdout test with data, which is the y test, against the predictions our model just made. Now let's plot this up. For that, you just need to type in plt dot figure, and in the braces just give the fig size, which is whichever size you prefer, which is equal to, let's say for me 6,4 is fine, and let's just run it. We set the size of our visual figure to 6 by 4 inches to ensure it is readable. Now, how to plot SNS heat map? So, let's say we have SNS, right? So, SNS dot heat map, and give the access to that, which is confusion matrix, comma, and note is equal to true, comma, FMT is equal to D, and comma, C map is equal to, let's say, blues, and execute this step. So as you can see here, it has given us a confusion matrix. This is the core visualization step. We generated a two-dimensional heat map, which is anode is equal to true and FMT is equal to D, which ensures the actual whole numbers are printed inside the squares. The C map is equal to blues. Oriented applies color variations where dark blue separates instantly draw the executive's eyes to our success zones, which is true positives and true negatives, while the lighter squares represent errors. Now let's just name the title as, let's say, PLT dot title, loan prediction, and confusion matrix. So let's just press enter after this. And as you can see, there will be a title which is loan prediction. There was an error in spelling. It says fix that. And there you go. You have a heat map to display to the people. We added a clear title as well to our chat so stakeholders know exactly what they're looking at. Now, let's say we have to add an X label. So, for that, enter PLT. Now, what is the name? We can give predicted as well. Predicted. And then, let's say PLT dot Y label and print actual. And then, if required, we'll just print show. PLT dot show. Now let's execute this. There's an error. Now can you see we have an X label as actual and predicted as a Y label. So the graph is more clearer which is predicted and which is actually the values that is printed. Finally, we display the rendered heat map to the screen. Now step 2 is visualizing feature importance as a bar chart. For that, let's start with importance is equal to model coefficient, COEF and bar. We grab the exact names of our columns, which is applicant income, loan amount, and also credit history, so we can label our chart. So again, we'll start with PLT dot figure and fig size. I'll give it a little bit bigger so you can see the difference. Let's say 8,5. Now here we have to create a new slightly wider figure for our next visual. Next, we have SNS dot bar, and then we are introducing features in that. So we have X is equal to feature, and then Y is equal to importance. And then also let's give a palette also. Palette is equal to, let's say, viridis. Now, when you want to illustrate comparisons between different categories, a bar chart is an absolute best choice. We pass our features into the x-axis and their extracted weights to the y-axis using professional color palette. So after this, the next step is to put on y label and x label. So we have plt dot y label and let's say importance and in brackets coefficient, which is coefficient and weight. This should be my Y label. Next, let's plot the X label as well. Now, what should be the X label? Let's just say features. And then finally, it is PLT dot. And now let's execute it. There are some errors in fig size. So just explain error. So as you can see, the bar graph, we have a X-axis, Y-axis, and we have a title as well. So here, can you see the differentiation of the palette as well? So step 3 is going to be the execution role play, which is the conclusion. Clear the code cells from the screen so that only the heat map and the bar charts are visible side by side. For the final part of this course, we are going to role play. You are lead data scientist presenting your findings to the bank's board of directors. You would point to the screen and say, executives of our goal was to automate loan approval safely. As you can see from the dark blue zones of the heat map, our predictive models automates this process with high accuracy. Furthermore, looking at our bar chart, the model reveals that we should prioritize marketing to applications with existing credit history. And with that, the executives approve your model for deployment.
Let's move on to Module 6, which focuses on model deployment and operationalization. Building a machine learning model is only a part of the overall life cycle. In many real world projects, creating the model is actually not the hardest part. The bigger challenge is talking about the model and making it usable in practical environments where real users, applications, and even business systems can benefit from it consistently and reliably. This is where deployment becomes important. Model deployment is an important process of moving a trained machine learning model into a production environment so it can start making predictions on real world data. Instead of remaining inside a notebook or experimental setup, the model becomes part of an actual working system. Operationalization goes even further. It focuses on maintaining, monitoring, scaling, and managing the model after deployment. A model may perform well during deployment, but real world conditions consistently change. Data distribution shift, user behavior evolves, and even system requirements grow over time. Because of this, deployed models need continuous monitoring and updates to remain accurate and useful. This module explores how machine learning systems move experimentation into production ready solution. It becomes concepts like serving models through APIs, integrating models into applications, managing infrastructure, tracking performance, and also handling issues such as latency, scalability, and also reliability. In modern AI systems, success is not measured by only how accurate a model is during a training period. A successful model is the one which can operate efficient in real environments, deliver prediction consistently, and continue creating value over time. That is why deployment and operationalizations have become essential skills in machine learning and AI engineering. One of the most important mindset shift in machine learning happens when moving from a notebook to the real world. During development, models are usually built and tested in controlled environments. The data is clean, static, and historical. Everything runs locally, experiments are repeatable, and achieving high testing accuracy often becomes the primary focus. Inside a notebook, the workflow feels predictable, data is already available, dependencies are controlled, and model only needs to perform well under expectational condition. But it does not fully represent real production system. The real world is very different. Instead of static historic data sets, production systems deal with continuous live data streams. Data arrive constantly, often with inconsistency, missing values, noise, or even unexpected patterns. Models must operate inside complex software ecosystems where multiple services, databases, APIs, and applications interact together. Another major difference is accessibility. A model may achieve excellent accuracy during training, but if it uses or systems cannot actually access it, then it creates zero business value. This is why deployment is so critical. Deployment is the act of freeing the model from the notebook environment and making it available for real world use. Once deployed, the model becomes a part of an operational system. Applications can send requests, receive predictions, and use those predictions to support decisions, automations, recommendations, or even business processes. At that point, machine learning stops being just an experiment and starts becoming a functional product. Understanding this difference is essential because real world AI is not about building accurate models. It's about building systems that are accessible, reliable, scalable, and also capable of delivering value continuously outside the deployment environment. Model deployment introduced a major paradigmic shift in how machine learning systems are designed and evaluated. During development, most machine learning work happens inside a local Jupyter notebooks. These environments are ideal for experimentation because they allow data scientists to test models, visualize results, and also iterate quickly. But production systems operate very differently. In development environments, models are usually trained using static CSV batches or historic datasets. The data is fixed, predictable, and already available before training begins. In production, however, systems often process real-time JSON streams where data arrives continuously from applications, users, sensors, and extreme services. This means the model must handle income requests dynamically instead of working with preloaded files. Evaluating those also changes significantly. In notebooks, success is often measured using static accuracy scores such as predictions, recall, and overall testing accuracy. While these metrics are important, they are not enough in production systems. Real world models require continuous health monitoring because performance can degrade over time. Factors like data drift, changing user behavior, or even infrastructure issues can affect how well the model performs after deployment. Even the overall goal changes. During experimentation, the focus is usually on finding historical patterns in the data and improving model accuracy. But once deployed, the priority shifts towards serving real time users' requests reliably and efficiently. A production model must respond quickly, remain available under heavy usage, and integrate smoothly with other software systems. This shift is important because production machine learning is no longer just a research program. It becomes an engineering problem as well. Success depends not only on building intelligent models but also on creating systems that can operate continuously, scale effectively, and also deliver predictions reliably in real world environments. Deployment is a process of integrating a machine learning model into a live production environment so it can receive real time inputs and also return actionable prediction. This is the stage where models moves beyond experimentation and becomes part of an actual working applications or even business system. A deployed model must be able to interact with real users, applications, or even services continuous. Instead of manually testing predictions inside the notebook, the system now receives requests automatically and generate outputs in real time. This allows machine learning models to support recommendation systems, fraud detections, forecasting automation, and many other real world use cases. One important concept is deployment is containerization. Containerization involves encapsulating the module and its dependencies into secure and uniform operating environments. Tools like Docker are commonly used for this purpose. Containers help ensure that the model behaves consistently across deployment, development, testing, and production system. With containerization, difference in software version and environments can create unexpected failures during deployment. Another critical component is web frameworks. A deployed model is often wrapped inside a server architecture that listens for incoming requests and returns predictions. Web frameworks help explore the model through APIs so external systems can communicate with it effectively. This allows applications, websites, or mobile platforms to send data to the model and receive responses instantly. Next, we have scalability, which is strategies are also essential in production environments. As usage increases, the deployment systems must handle larger volumes of requests without slowing down or falling apart. Model deployment architecture are designed to support scaling and redundancies so services remain available even during heavy traffic or system interpretations. Deployment transfers machine learning from an isolated experiment into a reliable operation services capable of creating real business value. One of the most important components in model deployment is the API bridge. APIs or application programming interfaces act as a communication layer between the user's application and the machine learning model. Without the bridge, most real world systems would have no practical way to interact with deployed models. The process usually begins with user interface. This could be a website, mobile application, dashboards, or even another software systems where users provide input for a request prediction. For example, a customer may upload an image, type the message, or even submit the transaction details. The application then needs a way to send this information to the machine learning model. This is where the API becomes essential. The API acts as a messenger between the application and the model. It receives requests from the web application, translates the data into format the model understands, and forwards it to the machine learning system for processing. The model then performs its task using the trained algorithm. Depending on the use case, it may classify data, generate predictions, determine anomalies, and also recommend product or even perform some other intelligent operations. Once the prediction is generated, the result is sent back through the API to the application. Finally, the user interface displays the actionable answer to the user in a simple and understandable way. From the user's perspective, the process feels almost instant, even though multiple systems are working together behind the scenes. The API bridge is critical because it allows machine learning models to become accessible and usable within the real applications. It connects software systems with AI functionality and enables machine learning to operate as a part of scalable real world products and services. Now, operationalizing a machine learning model means turning it into a usable service that can handle real world requests automatically. One of the most common way to do this in Python is by using Flask, which is a lightweight web framework often used for deploying machine learning models through the APIs. The first step is loading the model. After training is complete, the model is usually saved as a file so it can be reused later without retraining every time the application starts. When the Flask application runs, the pre-trained algorithm is loaded into the memory and becomes ready to generate predictions. The next step is setting the endpoint. An endpoint is essential a URL where external system often can send requests. Flask allows developers to create routes that listen for incoming data. In machine learning applications, these endpoints are commonly designed to receive post requests because users or applications are sending data to the server for predictions. Once the request reaches the servers, the application extracts the data. Most modern applications exchange information using JSON format because it is lightweight and easy to process. Flask retrieves the income JSON data and converts it to a structure the machine learning model can understand. After pre-processing the input, the model executes its prediction logic. Depending on the application, this could involve classification, regression, recommendation, and any other machine learning tasks. The generated prediction is then prepared for delivery back to the user or application. Finally, Flask returns the results as a response, usually in JSON format. This response travels back through the API and becomes available to application interface most instantly. This workflow is important because it transforms machine learning models into accessible services that can support real-time applications, automation systems, and scalable business solutions. One of the biggest misconceptions in machine learning is believing that deployment is the finish line. In reality, deployment is only the beginning of model's real-world lifecycle. Once a model enters production, it immediately starts facing conditions that are different from the historical data it was originally trained on. Machine learning models are built using past data. During training, the models learns patterns, behaviors, and relationships that existed at the point in the time. But the real world is constantly changing. Customer behavior shifts, market conditions evolve, business processes change, and also external events introduce new patterns that may not exist in the original training data. As these changes occur, the model's predictive accuracy naturally begins to degrade. This problem is commonly known as the model drift or data drift. A model that performed extremely well during the testing may slowly become less reliable over the time because the environment it operates is no longer matches the environment it learned from. This is why production machine learning requires continuous monitoring. Teams must track performance matrices, monitoring prediction, quality, identifying usual behavior, and retain models when necessary. Without monitoring, organizing may continue using models that are slightly making increasingly inaccurate decisions. Operational machine learning is therefore not one time task. It becomes an ongoing life cycle involving maintenance, evaluating, updates, and improvement. Successful AI systems are not simply deployed and forgotten. They are actively managed to ensure they remain accurate, relevant, and also reliable as conditions evolve. Understanding this reality is essential because real world AI systems must adapt continuously if they are expected to deliver long term business value. Model deployment does not end with making predictions available to the users. Once the model is running in production, it must be continuously maintained and monitored to ensure it remains reliable, accurate, and stable over the time. This is a critical part of operational machine learning. One of the most important areas of monitoring is tracking. Technologies such as ELK stack, including Elasticsearch, Longstash, and even Kibana, are commonly used to collect logs and diagnose production issues effectively. Another major focus is monitoring prediction, accuracy, and latency. Accuracy monitoring helps determine whether the model is still generating reliable prediction in real world conditions. Latency monitoring measures how quickly the system responds to requests. Even highly accurate models can accurate poor user experience of the predictions take too long to return. Production systems must therefore balance both intelligence and performance. Model maintenance also involves comparing prediction outcomes against actual real world results. This is one of the most effective ways to detect model drift. Over the time, the relationship between the input data and real outcomes may change, causing prediction quality to decline. By continuously evaluating prediction against reality, teams can identify when the retaining or updating the model becomes necessary. Operational AI systems require ongoing attention because real world environments are dynamic. Successful machine learning systems are not static deployments. They are actively monitored, maintained, and improved so they can continue delivering consistent business value even as conditions change over the time. Machine learning models are not meant to remain unchanged forever. As real world conditions evolve, models must also evolve to maintain accuracy and reliability. Repeat. As real world conditions evolve, models must also evolve to maintain the accuracy and reliability. This ongoing improvement process is commonly known as retaining the loop. The cycle usually begins with monitoring performance. Teams continuously track prediction, accuracy, and system behavior using dashboards and monitoring tools. The goal is to identify performance drops, unusual trends, or even signs of model drift as early as possible. Since production environments change over time, monitoring becomes essential for maintaining trust in models' predictions. The next stage involves assessing new data. Production systems constantly generate fresh real-world data from users, applications, and business processes. This new data often contains patterns that were not present during the original training phase. Collecting and analyzing updated dataset helps teams understand how the environment is changing and whether the model is still reflects current conditions accurately. Once enough updated data is available, the model can be retained and fine-tuned. During this process, the machine learning algorithms are rebuilt using the newer datasets so the model can learn more recent patterns and behaviors. Fine tuning may also involve just hyperparameters, improving pre-processing steps, or refining feature engineering techniques to improve overall performances. After retraining, the updated model must be validated and redeployed carefully. Teams need confirm that the newer version actually performs better than the previous one before replacing it in the production. This helps to avoid introducing unstable or lower performing models into the live system. The retraining loop highlights an important reality of operational AI. Machine learning is not a one time project, it is a continuous life cycle of monitoring, learning, and improving, and also adapting to changing real world environments. The operational life cycle of machine learning system goes far beyond simply training a model. In real world AI system, deployment is not just a destination, it is beginning of continuous operational life cycle that requires monitoring, maintenance, and consistent improvement. The process usually starts with training the model inside a notebook environment during this stage. Data scientists prepare data sets, build algorithms, evaluate performance, and optimize accuracy. This is where the foundational intelligence of the system is created. Once the model is ready, it is wrapped inside the API using frameworks such as Flask. The API acts as a communication layer that allows applications and extreme systems to send requests and receive predictions. This step transforms the model from a research artifact into a usable service. After that, the model is deployed into production environments, often using technologies like Docker containers. Deployment ensures the model can operate consistently across systems and support real world applications reliably. At this stage, the system begins serving user requests using real time JSON data or other live inputs. But the life cycle does not stop after deployment. Production system must continuously monitor health and performance. Teams track predictions, quality, latency, uptime, and also system behavior to ensure everything remains stable and accurate. Over the time, models begin experimenting drift because real world conditions evolve. When drift is detected, new production data is collected and used to retain the model. The updated model is then redeployed into the production, restarting the cycle once again. This continuous loop is what makes operational machine learning different from traditional software systems. AI systems must learn and adapt continuously to remain effective. Successful deployment is not just about launching a model once. It is about maintaining a living system that allows alongside the environment it operates in.
A machine learning model is only valuable if it can be accessed in the real world. Now let's train the model to save and deploy its live web application programming interface, which is an API using Python's Pickle and Flask libraries. So the first step here is to freeze and save the model. Now, what is the code for that? Follow as well. First things first is to import Pickle, and next is to save the trained logistic regression model to a file. So we have with open, let's say loan model dot pkl. This is the pickling model, and then followed by wb, which is a file. Next we'll dump it. So we have pick dot dump model comma file. And next, if this is successfully there, we'll just print done. So let's execute this. So there is a error. So let's fix it. And there is one thing I was saying. So let's fix that. And here we go. Still there is an error. Let's check what is the error. You can use Gemini also to figure out what the error is. So there was a space here, and let's just accept the mistake and run it. And the model is pickled. As you can see, you will see this loan model pkl. Just download this file to the app file, which you can create a new folder and you can just download it. Now it's downloaded in my downloads. I'll just copy this and paste it in my app folder. So I have an app folder where I have a file which already has the code, which I'll be explaining it soon, and paste it over that. Before we leave our notebook, we must save our trained model so that we do not have to retrain it from scratch every single time a new customer applies for a loan. To do this, we use Python's pickle model. This process of freezes our trained logistic regression model and saves it in a file. In this case, loan model PKL is that can be easily loaded into our web application. So the next step is to building the Flask and web API. So firstly, you need to create a notebook or Python IDE or any kind of blank text editor like VS Code or PyCharm to create a new script named AppPy. Now, what is the code inside that? Let's take a look at that. So firstly, here we are starting out with importing Pickle and NumPy, which are like the required libraries here. Then we are creating a Flask app, which is AAP is equal to Flask name. Then we are loading the pre-trained model here, which is model is equal to pickle.load, pen, and the model name. Next, the step 3 is to create prediction API, which is a router API and the prediction function. Next, we have df predict. Now here you can see we are extracting features from JSON post request where data is equal to request.getJSON post is equal to true. Next, we are organizing the data again here and also adding the features, which is the application income, loan amount, and also the credit history. And the final features we have put it in an array. And the last step, we are making the prediction using the loaded model. Now, what is a loaded model? It's pickle. So we know that. And then we have the last, which is prediction is equal to model.predict, the final feature. Next, we are convert prediction in human reliable JSON response. So here we are giving a command of approved if prediction is equal to 1, else denied. And then we are returning the loan status output. And lastly, we are run the live application, which is if name is equal to main, run the app. So let's just run this model and see what are the issues or if its system is running or not. So how do you run this? Again, command prompt and just check the location, copy it and cd location, enter, and then you have to give Python and the app.p1. So it will take some time to execute. There's a warning, but Flask app debug, it's fine. It's just a warning. So finally, what happens here is it'll ask the loan amount to be approved, your name and other details. So the model will calculate if your loan is approved or denied based on the information that you have provided to the model. And with that, the final deployment, we have successfully taken raw messy data and turned it into a automated intelligent business application. Congratulations on completing the data science lifecycle.
Congratulations on taking this massive step in your data science journey. Over these 6 modules, you have mastered the entire data science lifecycle. You didn't just learn the theory, you have learned how to act as a true data scientist. You started by understanding the mathematical engines of probability and statistics and moved on into cleaning and transforming raw, messy data, build a highly accurate predictive machine learning model, and also visualized your findings to drive business decisions, and finally deployed your model as a live web applications. You now possess the core skills to take raw data and turn it into automated intelligent business solution. But remember, data science is a field of continuous learning and practice. Take these scripts, download new data science, and start building your own portfolio of real world projects. Want to watch more insightful videos like this? Don't forget to like, share, and hit that subscribe button. Thank you for watching and keep learning with Simply Learn.